In this chapter, we'll look first at a definition of moment of inertia, calculation for a bicycle wheel, and then a percentage of the total contributed by the rim, the hub, the spokes, and the nipples, and then the tire. And there's lots of math. When we calculate weight of rotation, light is not always salvation. The inertia moment for each component depends on the mass's location. Because bicycle wheels spin, they have rotational energy, and part of understanding how that rotational energy is measured is an understanding a term called the moment of inertia, and that's what this chapter is about. Moment of inertia answers this question: how far is each component of the mass from the center of the wheel? We will compute separately the moment of inertia of the rim and the hub, the spokes, and the nipples. The moment of inertia, given by the symbol I, will be for the wheel the sum of the moments of inertia of the rim, the hub, the spokes, and the nipples. This graphic shows the shapes and the formulas used to calculate the rotational inertias of a variety of shapes. These are the only three we'll use for a bicycle, so we can cut out all the other ones, leaving us with just these three. This picture is a thin ring or hollow cylinder rotating about its axis. That's the picture we will use for a rim. This one down here is a disc or solid cylinder rotating about its axis. That will be used for the hub. Over here for the spokes, a thin rod rotating about its end. And up here, we'll use this symbol again for nipples. We're going to work through the entire wheel, and as we do, we'll fill in this table and show for each component the calculated moment of inertia. Let's calculate the rim first. The rim is represented as a thin ring rotating about its axis, and its moment of inertia, I, is the mass times the radius squared. Now this might be a 700C wheel. Let's just remind ourselves that 700C is a reference number. It's a dimensionless or unitless number, and it is not a measure of a distance. The same is true of a 650B or a 650C. This graphic shows us a wheel, and these are the hooks on the rim. Here is a tire installed, and these are the beads on the tire. Those lines represent the hook bead interface. And that distance there is called a bead seat diameter, which for a 700C wheel is 622 millimeters. We can often find this information on the tire and on the rim. Here on this section of rim we see 622, 19 is the width. Over here on the tire, 700 and 622 bead seat diameter. 25 represents the width of the tire when it's inflated in millimeters. For a 700C wheel, my bead seat diameter works out to a radius of 311 millimeters or 0.311 meters. Now for this graphic, which is obviously not drawn to scale, my radius would be from the center of the hub to either the inside of the rim or the outside of the rim or something in between, which I could laboriously calculate with precision. But the bead seat diameter is a pretty good approximation, and it's a number that's easily obtainable. For this wheel, let's use that as the radius of 0.311 meters, and we'll let the mass of the rim be 400 grams, which is 0.4 kilograms. My formula, I equals mr squared. Mass times radius squared. Plugging in those numbers, I get 0.0387 kilogram meter squared, and that is the unit that you'll see for moment of inertia. We'll put that into our table for the rim. Next is the hub. The hub is considered a solid cylinder rotating around its axis, and this is its formula. I could measure the hub's radius from its center at a number of places. I could measure it at the axle, at the lock nut, at this part of the hub shell, here where the flanges are, or over here where the free hub body is. If I assume that my hub diameter is as shown by these blue lines, then I would get this radius, and that is obviously not representative of the average of the radius and diameter of the hub. If we go through and we calculate what's called the centroid diameter, which would be this line here, then that would give us the smaller radius. I can treat this hub here as a cylinder with a length equal to the axle, but with a diameter equal to its centroid. So now I have a radius of 15 millimeters, or 0.015 meters, and I have a mass of 415 grams, which is 0.415 kilograms. Substituting my formula, the moment of inertia of the hub is going to be 1/2 the mass times the radius squared. If I substitute the above numbers into that, I get this expression here. And when I solve that, I find I get a moment of inertia of the hub of 0.0000466 kilogram meter squared. I could rewrite that as a power of 10, but I'm going to leave it like that for the time being. And we can enter that number into our table. Moving on to spokes, it's a thin rod rotating about its end, and that is the formula. There's my length of 306 millimeters. That is the mass of a spoke that I've measured on a balance of 6.85 grams. Now that is going to be for each of 24 306 millimeter DT Swiss competition spokes. There's my length, and when I plug this information into my formula, I can calculate the moment of inertia. Now, the mass is actually distributed over the length of the spoke. So imagine that I measure that distance and a unit point mass at that point, and do the same thing here and here and here and here and here, all over its length, all these little calculations. Then I could sum up the product of these little tiny increments of radius times the increment of mass at each point. If I were to solve that little calculus integral, and that would give me that 1/3 mass times length squared, which has already been worked out for us. When I take my formula for the spoke and I substitute the values for mass and length, I get this result, 0.000214 kilogram meter squared. That is per spoke, and that would be the total for 24 spokes, and we'll leave it written as you see here. And we add that to the table. Next and last are the nipples. The radius here is also 306 millimeters. We'll consider the nipples to be point masses on this thin ring, and therefore we'll use this formula for their moment of inertia. The nipples I'm going to use are going to have a mass of 0.98 grams or 0.00098 kilograms. These nipples are Sapim 12 millimeter brass nipples, and there are going to be 24 of them. The length of those nipples, the length from the hub center is 306 millimeters, which puts them right on the rim. And there's my formula, mass times radius squared. when I plug in the numbers for the mass and the radius, and I solve that, I get 0.000092 kilogram meter squared, but that is for just one nipple, and I have to multiply that by 24, and I get 0.0022 kilogram meter squared for the sum of the moment of inertia of all 24 nipples. Here we add them to our table. The moment of inertia of the wheel is the sum of those components. And when we add that up, we get 0.0461 kilogram meter squared. The reason I wanted to leave these calculations the way you see them instead of expressing them as powers of 10 is for ease of comparison. Now let's just put a line down here to indicate where the decimal point is. The moment of inertia of the hub, for example, is totally insignificant. In fact, the calculation is outside the range of any significant figures in the total. If we had not bothered at all with that discussion of the centroid diameter of the hub and just used a radius based on the flange diameter, we would have still found that the moment of inertia would be insignificant. And we can further illustrate this by showing for each component the percentage that it contributes of the total moment of inertia. And that is going to represent where the decimal points lie. The rim is 83.9% of the total. The hub is a mere 0.1, and the spokes 11.1, the nipples 4.77, and I get a total here of slightly less than 100% because of rounding. Let's see what happens when we put a tire and tube on the wheel. My tire is going to be a Michelin Pro 4 700 by 23C tire, 200 grams, and the tube is a specialized tube with a 40 millimeter Presta valve, 144 grams. I add that together and I get a mass of the tire and tube combined of 344 grams or 0.344 kilograms. The tire and tube is going to be considered a thin ring, this formula. Here's the now familiar formula. We plug in the data for the tire and tube, and we're going to have a length of 330 millimeters here. This is a little bit more clearly than the rim because we have to measure to the center of the tire. And when we plug those numbers in, we get the substitution for the mass and the radius squared. That calculates out to be 0.0374 kilogram meter squared for the moment of inertia of the tube and tire combined. We add that to the table. And we get a new total, and again lining up our decimal places. And we'll look at our percentages of the total. That's going to be where we line up the decimal points. And for the rim, we have 46.3%. For the hub, trivial 0.1% still. The spokes, 6.16%. The nipples, 2.63%. The tire and tube, 44.8%. And we add all that up, we get 99.99%. So from this, I can make a couple of observations. One is that combined, the rim, tube, and tire account for over 90% of the total moment of inertia. And the moment of inertia of the hub is negligible. Now note that I'm not saying that the mass of the hub is negligible, but its moment of inertia as a rotating part of the wheel is negligible.